গুড মর্নিং স্টুডেন্টস, আজকের তাহলে ক্লাসটা আমি এখন শুরু করছি। হ্যাঁ, স্ক্রিনটা একটা শেয়ার করছি, শেয়ার হলে একটুখানি আমাকে বলবে যে শেয়ার হয়েছে। শুনতে পাচ্ছ তো আমাকে?
Yes, ma'am.
Yes, ma'am.
ওকে ওকে।
Yeah, ma'am.
ওকে, okay. So this is the paper that deals with digital system design, and so far you have already learned how to design a system, or rather how to design a combinational systems only. I am going to cover the part mainly deals with the sequential system. Now here comes the question that you have already learned how to design or how to solve for a problem like addition, subtraction, these single operations. Okay, and you are almost now able to design almost anything. I mean, I can give you an operation, you can design the corresponding circuit that can perform that single task. So what is there in sequential circuits that we need to know about? First of all, what is it? And second of all, why is it? So you see, you have created the combinational blocks. But when you need to design a system, when you are designing a system, it can consist of multiple of operations. I mean, it is obviously consisting of multiple operations, because multitasking is a very important parameter for a system. Also, if you want to take a very simple problem like simplification, okay, suppose 2 plus 4, with that the result of that is needed to be multiplied with another 5, something like that. So in that case, you know how to design an adder, you know how to design a multiplier, but the sequencing of operation, that is which operation is coming after which, that thing you do not know until now. So these sequential circuits deal with that kind of things, that is sequencing. It determines the sequence between the operations. So far you have designed the combinational blocks like some isolated islands, and through sequential logic you are going to set up the link, that is which combinational block we need to call and when. So here you see, in case of combinational circuits, if you're asked to represent that through a block diagram, it will be simply like this. A set of inputs will be there, and you are getting, based on these inputs, you are getting some output. But when it comes to sequential circuit model, obviously we need this combinational block, but we need something extra, because here, depending on the previous output state, we are determining the present output state. So previous output states are needed to be fed back as one of the inputs. And to remember those previous outputs, obviously we need what we call a storage element, or in simple terms, memory. So this combinational circuits or combinational blocks with this memory, like this total thing is representing the sequential circuit model. And here actually lies the significance, that it determines the sequencing, it is creating the link between the separate individual combinational blocks. So now we will start from the simple element, simple memory element, that we call a latch. So here we can see that this is the simplest latch, we can say. These two symbols, from these two symbols you can easily say that this is NOR gate, and this is one of the universal gates. Now, before proceeding with this circuit, and we will see that how this is acting as a memory element, we are going to just take a look at the truth table of NOR gate. We are all well aware of this, but still, it is a bit of a recapitulation. Now, one thing I would like to ask you to notice that, notice carefully, in case of NOR gate, if any one of the inputs is 1, the output is inevitably 0. See, here it is 0, 1. One of the inputs is 1, so output 0. Here is also one of the inputs is 1. And in this case, 1, 1, obviously two inputs are 1, but that means one of the inputs are 1. So this is also 0. Only it will take one value when the input is 0, 0. So these things we need to keep in mind, that in case of NOR gate, when one of the inputs is 1, then the output will be 0. Now let us come down to this circuit. This entire thing, this entire block is what we call as the latch, and here it is NOR gate based latch. Two inputs are there. Suppose this is R, this is S, and output Q and Q bar. Now since there are two variables, obviously there are 2 to the power 2, that is 4 number of combinations that we can actually give as an input to this circuit. So let us first consider, suppose S equal to 0 and R equal to 1. This combination. Suppose S is equal to 0 and R equal to 1. S 0, R 1, or maybe we can consider this one. First it is 1, okay. This is 1 and this is 0. So what is happening? Since this is a NOR gate and we have already established if one of the inputs is 1, the output will inevitably be 0. So here it is 1, here it is 0. For this NOR gate, one of the inputs is 1, so the output will be 0 here. Now this 0 is fed back to this point. That is, it is one of the inputs of this NOR gate. Now this is 0. This is already 0. So 0, 0, output will be 1. And this 1 is coming down here. So here we are getting actually 1, 1 that corresponds to 0. So we are getting Q is equal to 1, Q bar is equal to 0 for this R and S input. When I am giving S is equal to 1 and R equal to 0. So one of the combinations is done over here. 1 and 0, in the output we are getting Q is equal to 1, Q bar is equal to 0. For the time being, please ignore this set and reset thing. A bit later, I am coming to that. Now, let us consider another condition. This 1, 0, it is immediately followed by 0, 0. That is, 1 here is changed to 0. And this remains as it is, 0 to 0. So now the input here, it becomes 0, it becomes also 0. Now from the previous output, that 1 is fed here. So here, still, one of the inputs of this NOR gate remains 1. So output will remain unchanged. That is 0, it was the previous one, and the new output is also 0. So here the 0 is being fed as one of the inputs. Now it is becoming 0 and 0. So 0, 0, that means here it is 1. Okay. So if 1 0 condition is followed by 0 0, we are saying that this actually is holding the previous state. That is no change in the output. It is 1 0, it is 1 0. Just a minute. Okay, Ravi Kumar, what is the name? Ravi Kumar, please switch on your mic. Ravi Kumar, can you hear me?
Yes, ma'am, I can hear you.
Okay. Next time, please try to enter the class in time because it is really distracting like this. Okay, today I'm only allowing you, but please maintain time from now on. Okay.
Okay, ma'am.
Okay. Okay. So as I was saying, that this 1 0 condition, when it is followed by 0 0, it is actually holding the previous state. So this 0 0 condition can be termed as memory, but it is only we have checked that this is happening for 1 0 if 1 0 is followed by 0 0. Is it happening for the other conditions as well? Let's see. Now we are just changing the input to 0 and 1 like this, 0 and 1. So can anyone tell me that what should be the output and why at this stage?
Ma'am, Q will be 0 as there is 1 entering from R.
Okay.
And since Q becomes 0 and S
Mm-hmm.
is 0, so Q bar
Mm-hmm.
will be 1.
Okay. So the output state is changing or not?
Changing, yes.
Changing. Fine. Everybody is agreeing with him?
Yes, ma'am.
Okay. Now, please put another 0 0. I'm leaving it to you to check that if the 0 0 condition comes after 0 1 also, then it will remain, the output remain the same, that it will hold the previous state. Okay, this bit you will do by yourself. Is it happening or am I wrong?
Yes, ma'am, it is happening.
Okay, so we have established three conditions: 1 0, 0 1, and 0 0. And in both the cases, we have seen if these two conditions, that is 1 0 and 0 1, is followed by the 0 0 condition, we are actually getting a memory state or a hold state. We are still yet to explore the condition 1 1. But before that, let us explain these terms set and reset. Now, in digital electronics, the set is used in case the particular output has achieved high state or logic 1. Logic 1 means here 1. So you see here Q is attaining a value 1 and Q bar is attaining a value 0 when the S is 1 and R is equal to 0. So this state S1 R0, that corresponds to a set state. That means output, at the output is it is producing a set state. Similarly, when S equal to 0, R equal to 1, the output is achieving a value of 0, but the Q bar or complement of output is achieving a value 1. So this entire state is called as reset state. So for this condition, it is producing a reset state. And for 0 0 condition, since it is doing nothing but holding the previous state, all we can say that this is a hold state or a memory state. So this circuit is actually performing as a memory element when it comes to a particular combination. In this case, it is 0 0. Now, why the name latch? The latch means either it is producing 1 or holding 1, or it is producing 0 or holding 0. So as if it is getting latched to that particular value. That is why it is named as latched. Now we are going to explore the fourth condition, that is 1 1 condition. So if you give 1 is equal to 1 and r equal to 1, what will be the output? You see here r equal to 1, is equal to 1. So one of the inputs of this NOR gate is 1. So both the output should be 0, right? Q should be 0, Q bar should be 0.
Yes, ma'am.
Okay. So is it right or is it wrong? Is there any problem in there or not? Can anyone tell me? Is there any problem in there if I give both the inputs as 1? At the output, I am getting 0 and 0.
Q and Q bar cannot be 0 at the same time.
Why?
Ma'am, if
Ma'am,
it gets
both are
0, then all the
complementing
other
each other.
stages get unstable.
How? How? You are right,
Ma'am,
but how? Please
ma'am,
explain.
Ma'am, Q is complement of Q bar, so both cannot be Q.
Okay, Q is complement of Q bar. But you see, instead of naming it Q and Q bar, we could have given the name like A and B, right? I mean, nomenclature should be
Yes,
based
ma'am.
on the result. It is not the other way around. Since we have put the name Q and Q bar, that's why the output has to be the complement with each other. It is not like that, right? Doesn't make sense. Acha, do one thing. Please follow this condition with 0 0 and see what happens.
then both will be 1.
How? Both will be 1. How?
Uh, because both the inputs to both the NOR gates are zeros.
Mm,
Because Q is 0, Q bar is 0, AC is 0, R is 0.
okay. But you are forgetting one thing. And that thing is the delay that each signal suffers. I mean, here I am changing this to 0. Here I am also changing this to 0. So that should reflect the output after this bit delay. This amount, it will take some time to reflect that in output, right? So these two, suppose this is reflecting first. এখানে আমি 0 বসিয়েছি, তার জন্য এই আউটপুটটা ফার্স্টে চেঞ্জ হয়ে গেল 1, তাহলে তো সেই 1টা আবার এখানে চলে এলো, রাইট?
Yes, ma'am.
তাহলে সেক্ষেত্রে কি হবে? You basically cannot say যে which NOR gate is reflecting the change of input first. Can you say that accurately? No, I'm saying that this gate is going to change. No, you cannot. Because that amount of delay that it is going to suffer from traveling from input to output, that is actually unpredictable. You don't know. Even if theoretically we are using two same NOR gates, but still in practice, when you are using two gates, it is suffering most likely different amount of delay. Even if the difference between these two delay in the order of nanoseconds, but still it is very likely that this would be different. And also due to some maybe some thermal fluctuations in outside, it might happen that it affects the circuit performance. After all, within this gate it is a combination of transistors, mainly MOSFETs. So obviously that temperature fluctuations or any kind of night that is going to affect the inner circuitry. So you cannot predict which one is going to first. সাপোজ তোমরা ধরো কাজ করছো, দুটো আইসি নিয়েছো, যদি একটা আইসিতেই পাওয়া যায়, কিন্তু সাপোজ একটা আইসিতে একটা গেট খারাপ, ইউ আর টেকিং অ্যানাদার আইসি। একটা আইসি দিয়ে অনেকটা কাজ করেছো, সেটা খুব গরম হয়ে গেছে, এবারে আরেকটা আইসি থেকে তুমি এই সেকেন্ড গেটটা নিচ্ছ, সেটা কিন্তু এখন অত গরম হয়নি। সো ইন দ্যাট কেস অবভিয়াসলি ইউ ক্যানট সে যে কতটা অ্যামাউন্ট অফ ডিলে সাফার করবে। So basically what is happening when this 1 1 condition is followed by 0 0, you don't know what would be the output, because that will depend on which gate is reflecting input to output first. So যদি আমার ফার্স্ট ফ্লিপ ফ্লপটা চেঞ্জ করে তাহলে this would be 0, sorry, this would be 1, আর যদি সেকেন্ড ফ্লিপ ফ্লপটা চেঞ্জ করে then q bar would be 1. So you do not know. And anything, any result or any output that we cannot predict properly, that is totally undesirable, because that adds up unreliability to the entire system. You have designed maybe this RS or this SR, you have designed this is a part of a huge system. Okay, so here somehow this 1 1 condition appears, it gives 0 0, fine, up to that fine. But if you need to hold that particular result, you will give 0 and 0, but what it will hold after that you never know. So that is why it should be avoided, or in alternative term it is called a forbidden condition or not used condition. Clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so now if we try to construct the characteristic table of this typical SR latch. SR means set reset, so either it is giving a set output or it is giving a reset output, and it is giving a memory output. So basically SR stands for set reset. So 0 0, it is a memory condition. 0 1, at the output is giving 0 1, it is a reset state. 1 0 is corresponding to set state, and 1 1 is a not used condition. Now here please note that I am not saying that the truth table of SR latch, but I am saying that a characteristic table, because here you see, since there is this feedback mechanism, that is output is being fetched as one of the inputs. So here it is not like based on this 1 or 0 values, the data input solely the output is happening. No, it is not. It is depending on the previous state. So that is why, as if we are establishing the characteristics of that particular circuitry through this table. So it is called as the characteristic table. But in many of the books you will find that they say that truth table of latch or truth table of flip-flop. So they loosely say that, but very strictly speaking it is the characteristic table. Okay, so far we have seen the thing with the circuitry or the latch with NOR gates. Now there is another universal gate, that is called the NAND gate. And in NAND gate, if we want to design the latch, it will be something like this. The configurations will remain same, only the gate will change. And here you see the nomenclature will be like this. Now as it comes to nomenclature, here I am giving here R, giving here S. The logic is when S is 1, then we should get the set state, that is Q is equal to 1. So that is why accordingly this S and R name is given over here. Now if someone gives put a name R here and S here, then actually this circuit will turn or will behave in a way that when R is equal to 1, then only it will attain this set state. So it is a kind of non-conventional thing. So it is always better to follow this convention, that is when S equal to 1 corresponds to set state, I am getting a set state out at the output, that is Q equal to 1 and Q bar equal to 1. So in exams books often you just confused between these two, and sometimes you put R here, S here, but table you write following this. So please be careful about this nomenclature. Now in case of NAND gate based latch, here the nomenclature will be this. Why? This actually gives the complementary result of this. See, if this is S and this is R, I am putting 0 0 over here, it actually becomes a non-used condition, that is equivalent to the 1 1 condition in NOR gate based latch. And if 1 condition I put over here, it stands for the memory condition. That is the 0 0 condition in NOR gate based latch. And the set and reset state, they are just reverse. When S equal to 0 and R equal to 1, I am getting the set state, and when S equal to 1, R equal to 0, I am getting the reset state. So that is why this entire thing, this is alternatively called S bar R bar latch. So the output, if you here construct another two columns, S bar and R bar, it will, when S bar becomes 1, then it will give the set state, and R bar becomes 0, I mean 1, it will give the reset state. So according to that. Now here, since it is NAND gate, if we carefully observe the truth table of this NAND gate, we will see that if one of the inputs is 0, then the output is 1. Otherwise, the output is 0. Unlike the NOR gate, here if you put one input 0, you are getting output as 1. So based on that, this entire logic we have worked out. And here the same logic will be worked out, only here the condition is what? If I put any one of the inputs of this NAND gate as 0, at the output we will get 1. So you do this by yourself in home and check whether you are getting this characteristic table or not. Okay, this I am leaving as a reading assignment for you. অ্যাপ্রোচ একদম সেম থাকবে, শুধু একটু কেয়ারফুল হবে যে এখানে কন্ডিশনটা জাস্ট রিভার্স, অ্যাকর্ডিংলি করবে, এইটা ইউ শুড গেট দিস ক্যারেক্টারিস্টিক টেবল। ওকে, now we are moving on to next part. What is the next part? Obviously our aim is to design a memory element. We have to some extent design a memory element, because here in this circuitry for a particular condition it is acting as memory. But there are something that we need to talk about, some issues. First of all, obviously this not used condition. It is not desirable to have some forbidden condition or not used condition in our circuitry, because by human error or by some by means of some noise, it might happen this not used condition arrives after all. So to avoid it permanently, we need to adopt some scheme. Second one is, here we are getting either 1 0 or 0 1 as the output. So for the output here, Q, if we want to store this 1, then actually what we need to do, we need these two bits, S value and R value. A specific combination of this S and R value is only be able to store one bit, that is either 1 or 0 at the output. So that is kind of illogical. You see, if suppose you are asked to store a pencil in a pencil box. So if you need to put an eraser in addition to that pencil in order to store that single pencil in pencil box, then that is kind of illogical. We want to simply put the pencil in pencil box and it is stored. So here also, if we want to store 0, we want to give 0 as input, and if we want to store 1, we want to give 1 as input. We don't want to give a combination of 0 and 1 as input. So here two inputs are actually needed to store one bit. That is the second glitch. Another thing is, some sort of control we need to choose, that is when the input change is actually influencing the output. You see here, if 0 1, this is the condition. Now certainly, whether we want it or not, due to some noise, this 0 is changed to 1. Then what will happen? This entire condition will change, and immediately after a certain gate delay, obviously the output, this change in input will reflect at the output, and accordingly output will behave. So that we don't want. We need to put a control so that, like a gate, suppose. So when the gate is open, the change in input will influence the output, and the when gate is closed, then the change in input won't influence the output. So it is like that to hold something. Okay, suppose we want to hold this 1 0 condition, we need to put here 0 and 0. It is not that if we just remove after giving 1 0, if we change it to any value, it remains as 1 0 until and unless we want to change it. It is not like that in this present situation. So we need to adopt an additional control that will ensure that enabling that reflects the change in input to the output, and disabling that no matter what happens here and here, that stage, that output stage will remain constant, that it will be at memory stage. So these three are actually the glitches when it comes to this simple latch circuits, whether NAND gate based or NOR gate based. So now we will try to remove these glitches one by one. So first there is a concept of clocked latch. It is also known as flip-flop. Now what is clocked latch? Clocked latch is nothing but putting that additional control that we have just talked about in previous slide. The third point, the additional control. Clock will be that additional control that when I enable it, the change in the input will be reflected in the output, and when I disable it, I don't provide any clock signal, then the output will hold its previous state no matter whether input is changing or remaining constant. So here in this design we have used simply as the AND gates. So here when the clock, this signal becomes 0, then the output of these two AND gates will be 0, whatever be the value of S and R. And when it is 1, then the value of S and the value of R will propagate through these gates. So it seems pretty simple. But when I am actually disabling these two gates by putting a 0 here, then what is actually happening? It is a NAND gate based latch. Okay, this portion. So here actually it is attaining the 0 and 0 condition. Now 0 condition in case of NAND gate based latch is the not used condition. That is, we need to avoid it if we can. So here exactly in the disabling period of this clock, that 0 condition is appearing over here. So that we need to avoid. So we cannot use AND as that controlling gate over here. Instead, if we use NAND gates, so when it is NAND gate, that means when it is 0, the output will stick to 1. And when it is 1, the complement of this, if it is 1, then it will be 0. And if it is 0, it will be 1. The complement of these inputs are actually propagating. So here if we try to write the characteristics table, what will be it? When clock is disable, no matter what is the value of S and R, so I am putting a don't care over here. The output, that is S star and R star, will always be 1. And when S star and R star is 1 over here, this is actually the memory state. Why? Here in NAND gate based latch, this is actually serving as the memory state. So here it becomes the memory state. Also, if I enable the clock, I'm giving 1, and if we set S equal to 0, R equal to 0, the value of S star and R star will still be 1 and 1. So this condition also serves as memory. So these two conditions here is actually serving as the memory of this entire block. Now let us come down to 0, 1 condition. That is S equal to 0, R equal to 1. Now throughout I am enabling the clock or giving a high signal here, 1. So when I am putting 0 over here and 1 over here, the S star and R star, it simply will be the complement of this. because it is NAND gate. So that will be 1 and 0, and that corresponds to 0 and 1, that is reset state in NAND gate based latch. You see, if this is S equal to 0 and R equal to 1, at the output I am getting this 1 and 0, and this equal to 1 and this equal to 0. At the output I am getting 0 and 1. So that is exactly happening over here. If we change it to 1 0, the same thing will happen, and at the output I am getting 1 and 0. So now the thing is, if you just omit these two columns, A star and R star, now if you see SR as input of this entire block and Q bar as output, you will see that when S equal to 0 and R equal to 0, it is producing the reset state. And when S equal to 1 and R equal to 0, it is producing the set state. So no S bar R bar concept is coming into play. Here S and R is actually living up to its nomenclature, set and reset. When set input is high at the output, I am achieving a set condition. When set input is low at the output, I am achieving the reset condition. So this works like that. That is why NAND gate latch, it is one of the reasons why we are proceeding with NAND gate based latch. Now this entire block over here with S, R, clock as inputs and Q and Q bar as output, this entire block is what we call as flip-flop. And here it is set, reset, flip-flop. Why it is flip-flop? Because now an additional control, that is clock, in the name of clock, it is used. So this is set, reset, flip-flop. Now this is a clock waveform. If we try to draw the clock signal against time, it will be something like this. Now one single clock period means here to here. So one single clock period is actually consist of some amount of disabling and some amount of enabling period. Okay. So now if during this enabling period of the clock cycle, the input changes suddenly, S and R value changes in this time, so that will definitely affect or influence the corresponding outputs over here and hence over here. So here also, although we have imposed an additional control, but still we have to be careful that the input should be stable within this enabling clock period. Otherwise, there is a chance of the noise might hampers the output of the flip-flop. So some sort of control is there, we have established that, but still here the time duration over which we have to be careful to keep the input at a stable state is less now compared to that of the latch. So that is one minor advantage we have gained by introducing this clock. Now let us try to solve this. 1 bit is needed for storing 1 bit instead of 2 bit. So if you see this S, R, Q bar, this block, here if S and R are joined through a NOT gate, as is seen over here, through a NOT gate, this entire block here, it is shown as a single block like this. So now if these two inputs are connected through a NOT gate, then actually what we are getting, and this is the single input of this entire block, then what we are achieving, if we put the value 1 over here, it is automatically it is taken as 1 and 0 as input. And if we are putting a value 0 in here, automatically it is taking 0 and 1 as input. So when I am giving D is equal to 1, actually it is getting 1 and 0, and eventually at the output I am getting Q is equal to 1 and Q bar is equal to 0. And when I'm giving D is equal to 0, then at the output I am getting Q equal to 0 and Q bar is equal to 1. Okay. So here we have achieved that we only need this one bit in order to store one bit, either 0 or 1 at the output. So we have solved that second glitch that we have already discussed. Now here D stands for data or delay. Why data? Data means simply it is storing the data or storing the bit, and it is delay means at the input I am giving 0, at the output I am giving 0. So all it has to do, it has to suffer the amount of delay this total circuitry offers. So in some cases we need to deliberately introduce delay in order to maybe synchronize one signal with another, or in order to equalize the delay that is traversed by two certain signals using different circuitry path. So for that purpose, we need to introduce that kind of delay. So it is serving that purpose also. Now note another thing, that since I am here uh, connecting these two inputs through a NOT gate, either 1 0 or 0 1, only these two states will arrive. No chance of arising 0 0, no chance of arising 1 1. So here actually we have successfully avoided this not used condition. But then you will say the memory condition is also being avoided. But here, when the clock is 1 and SR is 0 0, this memory condition is avoided. But not this one, when a clock is disabled and inputs are don't care. So memory, it can still perform as memory element if we put clock equal to 0. Now there are some terminology what it is often asked in Viva questions. Suppose at this stage you are asked that please tell me that how many inputs and outputs are there in a single flip-flop. Then what would be your answer? See, in this case, we have mentioned flip-flop, okay? So here I'm seeing as input, I have got this clock signal, and this SR, or for this case, one input that is D. So one input that corresponds to D or that SR, these are termed as the data input. It deals with datas. Another input is clock input. That is, we just have introduced to convert a latch into a flip-flop. This clock input. And there are two other kinds of inputs that we will discuss a bit later. And outputs, for outputs, we have two outputs. So until now, we have seen data inputs, clock inputs, and two outputs. And we have solved to some extent the need of this control, this second glitch, and conditionally we have solved this first glitch. Now let us see that if we can actually use that 1-1 condition. Let us consider this circuit. Here the latch is given, that AND gates are given, this total thing is the flip-flop. But instead, one additional thing is done here, a feedback from the main output, the final output, to the first input. See here, this Q bar is fed back as one of the inputs of this NAND gate, and this Q is fed as one of the inputs of this NAND gate. So let us now see that if we put this 1 and 1, and also we keep the clock enabled, what exactly is happening? Suppose we are assuming the previous state is Q is equal to 1 and q bar is equal to 0. This q is equal to 1 and q bar is equal to 0. So here this one is fed back here, and no, this one is fed back here, and this 0 is fed back here. Now previously, so now actually what is the input of these two NAND gates? This is 1 1 0, because this 0 is fed here, so it becomes now 0. And here 3 of the inputs are 1, because clock is 1, R and S are 1, and now which is being fed back over here, that is also 1. So 3 inputs are 1. So naturally the output of this would be 0, and here one of the inputs is 0, so output of this is 1. So now here I am getting 1 and 0. This is a NAND gate based latch, so when it is 1 and 0, in the output we will get 0 and 1. So during the enabling period of clock, it is changed its state from the previous one, that is 1 to 0, and here from 0 to 1. That is, the output is become just the complement of its previous state. Now it is changed to 0. So now this 0 is fed back here. So this one, which was the previous input, has now become 0. And this is now 1. So this 1 will come here. So previous 0 is now becoming 1. So the inputs are, for this gate, it is 1 1 1. And for this gate, it is 0 1 1. So what is happening? This is 3 inputs are 1. So output is now becoming 0. Previously it was 1. Now it is becoming 0. And it was previously 0. And one of the inputs now becomes 0. So the output is changed to 1. So this 0 and 1 condition now. So the final output, this would be 1 and this would be 0. 0 and 1, that corresponds to 1 and 0 condition. Again this will be fed back like that. So if we continue keeping this clock 1, S equal to 1 and R equal to 1 throughout this entire enabling clock period, this will continuously change its states from 0 to 1 to 0 to 1 to 0 to 1, like that. And we won't be able to control this change of state until and unless we put a 0 over here. So this particular thing is what we call as the race around condition. What is race around condition? Race around condition is that where the output changes its state continuously without any type of controlling. We cannot control this, that how fast it is going to take or how many pulses will appear over here, we cannot control it. That will depends on the gate delay and some other factors of circuitry, but that total number of pulses remains unpredictable. So this is something race around condition, and a condition that we are unable to control. So one condition here is producing something which might be useful if it would have been controlled. But since it cannot be controlled in this present situation, we cannot say that we have produced a useful condition. So here the characteristic table of this entire circuitry now will become something like this. All these four conditions rather will remain same. Only this this condition will correspond to race around condition instead of being a not used condition. We are specific now what kind of error it is producing. For this circuit, it is giving rise to race around condition. So we have put it like that. Now, can we do some modifications to this circuitry to ensure that this race around condition can be controlled? Suppose we want this change of state must take place once in every clock period. Is it possible? If we achieve that by means of putting any kind of additional mechanism, if we are being able to achieve that, then that will be something useful. And that condition is what we call as toggling. When we say output is toggling, that means it changes its condition but in a controlled manner, and that control is actually in the hand of the user. And what is race around condition? That is uncontrolled toggling. That is race around condition. It is uncontrollable, but toggle is controlled. That we are fixing that for each clock period, the change of state that will take only once. So let's see whether we are being able to achieve that sort of toggling out of this circuitry. Okay, this is the same slide, this one. Here we are introducing another scheme, the master slave scheme, or what we call as the master slave flip flop. Now, what is master slave flip flop? Here you see we are actually implementing two flip flops, two individual flip flops, this red one and this blue one. We are giving clock to these individual flip flops as well. They are actually connected in series. One flip flop is followed by another flip flop. And here clock is also given, but the thing is, the clock to the first flip flop, when it is connected to the second flip flop, it is coming through a NOT gate. That is, here the clock bar signal is applied, and here the clock signal is applied. And here also from the final output, we are getting this feedback conditions as in case here, as in the previous case, we are getting a feedback. But here only the input of first flip-flop is actually getting the signal. The input of second flip-flop, it remains two input NAND gates. So this is the arrangement of this entire circuitry. Now let's see what happens. We want to change the output states, that is this output and this output, once per unit clock period. So you see the principle here. If we notice this waveform, for the enabling period of this clock, the flip-flop 1 is activated, but flip-flop 2 is deactivated. Why? Because when it is 1 over here, it is 0 over here. So it is disabling this entire thing. And when this becomes disabled, this becomes 0, this becomes 1. So on the next half, the flip-flop 2 is enabled while flip-flop 1 is disabled. So this kind of thing is happening. So throughout this entire one single clock period, for one half flip-flop 1 is enabling, for another half flip-flop 2 is enabling. Now let us investigate the previous condition. Suppose, okay, the same slide. I think we can use this. So here it is S and R are maintained at 1. At first clock is given 1 over here, and initially we have assumed the value here at the final output, here it is 1, here it is 0. So now the 1 is coming over here and 0 is coming over here. So the input of this NAND gate, it is 0 1 1, and this is 1 1 1. So obviously the output of this NAND gate would be 0 and this NAND gate would be 1. So here it is getting 1 and 0, and that actually reflects at the output of this first flip-flop, that is denoted as Q suffix M. So here accordingly we will get this QM would be 0 and QM1 is equal to 1. But until and unless this clock period or this clock signal here becomes 1 from 0, until then this Q and this Q bar won't be able to progress or won't be able to propagate through this flip-flop. So it will, this output of this flip-flop 2 will remain at this 1 and 0 output. Although the inputs are changed, but here we need to allow it by enabling it or by putting a signal 1 over here. Until and unless we are doing that, no change in output will happen. Fine. Now, here from 1 this goes down to 0. When from 1 this goes down to 0, this is actually changing its state from 0 to 1. So now it is enabling this entire flip-flop. So now the input it will see is 0 and 1. This will be reflected. Here 1 will come, here 0 will come, and I am getting this 1 0 condition. 1 0 condition here means at the output I am getting 0 and 1. See, here the change of state of output is happening from 1 to 0. So as the output is changed, this value is now fed back here. So from 1, now it is taking a value of 0. And here also, from 0, it is taking a value of 1 because output is now changed from 0 to 1 over here. So it is now becoming 1, 1, 1, not 1. Here it is becoming 1, 1, and here it is becoming 1 and 0. So it will then be able to propagate through these gates until and unless this becomes 1 again. Now what will be the input? At this instant it is 1 1, but the clock is 0, and here it is 0 1, but the clock is 0. So this new change, that is 0 here and 1 here, won't be able to propagate and reflect or affect or change these outputs. Now in next clock, when the clock again goes 1, it becomes 1, it becomes 0 to 1, then only this changed value will be reflected through this. So you see, throughout this entire clock period, if we look at the final output, that is QS, the change of state is actually happening once. So here if we try to draw this timing diagram for this entire clock period, you see QM is changing when it is going high. So here it is dropping from its previous value 1 to 0. And it won't reflect this to the output. So it will maintain its previous value. It will change its state when actually the clock is disabling itself. So it comes down to 0. So in this way, if we continue, it will give rise a waveform like this. So you see, per clock period only this change is happening once. So finally, we have achieved something useful out of this 1-1 condition, and that is the toggling. So here this entire block now is called a JK flip-flop. That is this flip-flop 1 plus this flip-flop 2. If we consider this as an entire block, we have got this input, these two data inputs, this one clock input, and these two outputs. So this is entirely called as JK flip-flop. If we try to write the corresponding characteristic table, it will be something like this. Here if clock is 0, it serves as memory condition. Clock is 1, J and K, here it is J and here it is K now. If these two are 0, again memory condition. Now for clock is enabling, but J it is equal to 0, it is equal to 1, it will give rise to reset. It is 1, it is 0, it will give rise to set. And when it is 1 and it is 1, it will actually give the complement of the previous state. So I'm just writing it Qn plus 1, which is the previous state, and it is being complemented here as present state. So Qn minus 1 bar, sorry, Qn minus 1, not plus. Qn minus 1 bar, and here it is Qn minus 1, because it is the double complement of this. It is Qn bar. So this is the entire characteristic table of a JK flip-flop. So far we have seen the importance of or the significance of the sequential circuits. Actually, to set up a proper sequence between different isolated combinational blocks, we need this. Without this, we cannot design a system as a whole. Because a system means it involves multiple number of operations to take place. Then a simple element, memory element, we have introduced latch. We have discussed about designing a latch using two universal gates, and what are the glitches, that what are the drawbacks of this kind of latch. Why cannot we use, although the main plus point, the main beneficial thing about this latch is its enormous simplicity. So even if we are getting a simple circuit with minimum number of circuit gates or circuit components, still we are not actually favoring it. Why? Because of the glitches. So from that latch, we have imposed control over here in the form of clock signal. That is actually giving one stage of advancement, or in modern terms, you may call it an upgradation. So here it is now becoming, from latch, it is transforming into flip-flop. SR flip-flop we have seen, and there also we have introduced another kind of flip-flop, that is data flip-flop. And after using data flip-flop, we wanted to use that 1-1 condition in some way so that we can produce something useful out of it. So we have arranged a circuitry like this, and we have used that 1-1 condition in order to ultimately produce a toggling action. Toggling action means, here you see, in each stage the complexity of the circuit is increasing, and the number of elements that is used to solve a specific glitch is actually increasing. So it is making the entire circuit complex, but in terms of what? More number of components means more amount of delay. That is, in each case it has to suffer from this input to this input, it has to go through this flip-flop and this flip-flop as well. So the delay is increasing. And also another additional gate, this NOT gate, is coming over here. So from here to here, it will suffer some amount of delay, because no reflection of input to output is instantaneous. Some amount of delay, and here we are not considering the wire delay. If the number of components is increasing, the wire length is also increasing, or more number of wires is needed to connect or to establish a secure connection. Here, even if we neglect that wire delay, we cannot neglect the gate delay. So with each stage, we are actually heading for more complexity, we are actually heading for more delay. That is, speed is hampering, but we are actually increasing the multifunctionality also. Another thing, with each stage actually, since the number of gate is increasing, the number of components on a single chip is increasing, or a single IC is increasing. So that means it might happen that the total area covered, or the total area needed for that particular operation is increasing. So ultimately it will come down to package density. Or we need to increase the area of the chip. It might happen, the package density is increasing, and we might have to sacrifice the area as well. Sacrificing means we need to increase the area a bit. So the portability factor, we need all the electronics gadgets we need in a very compact and portable way, but here the portability factor might have to be sacrificed a bit. So you see, here a lot of parameters are coming into play. If we are heading for multifunctionality, then might be the portability needs to be sacrificed. Also, if we are just going for simplicity, we might have to sacrifice the multifunctionality feature. So ultimately it comes down to the application, what kind of application we need to build up. Depending on that, we will impose all these conditions. So there is no best solution, it is always an optimized solution. it is optimized. When we say the thing is optimized, that means uh, this is the most we can get out of that circuit when these factors are needed to be considered. Some factor may be sacrificed, some factors may be enhanced, but we cannot ensure a circuitry that can satisfy all the parameters, and also without sacrificing any other parameter. We cannot design that kind of system. So there is no performance or no terminology like this is the best design or this is the best performance. There always a term which we call as the optimized design or optimized performance. So now if we just want to use the toggle mode of this JK flip-flop that we have established so far, if we want to use that toggle mode, means at the input we will give 1 and at the output we want the change of state. So here if we short these two inputs J and K like this, so here if we give 1, we will get the change in state, that is toggle mode, and if here T is placed 0, it will serve as the memory mode. So this is the characteristic table of this T flip-flop. Here T stands for toggle. It is a modified JK flip-flop where we can easily convert this JK flip-flop into T flip-flop if we simply short these two inputs and the clock is given outside. So inside this block, this entire circuitry is there. This master slave flip-flop scheme and everything. Now let us come down to this slide. As I was also mentioning before, that what are the parameters or what are the factors, not as an engineer point of view, from a consumer's point of view, what kind of factors we need from a system. Obviously, we need speed, compact size, obviously it should be very portable, and definitely multifunctionality. Now, if we see this map, if we aim for this compact side, that means the device dimension that makes or those are used to make a single gate. The individual device dimensions, either we have to scale down or we have to use less circuit components, that is less number of gate. Any one of this approach and it will lead to this compact size. So if device dimension has been scaled down, we cannot infinitely scale down the device dimension. We know the basic or the base element for a gate is always a CMOS, and CMOS consists of an NMOS transistor and a PMOS transistor. Now scaling down of the device means we have to scale down the individual NMOS and PMOS. So you have already studied, I guess, in your class of MOSFETs or semiconductor physics, semiconductor devices rather, that when we scale down the device dimension, mainly the channel length scaling, beyond certain value, certain adverse effects come into play that we call as the short channel effects. Now these short channel effects mainly lead to some leakage current, or it increases the off state power. That is when theoretically we are switching off the device, still some amount of current is there at the output. It is not getting instantaneously switched off. And since at the off state, some amount of current is there in the output, there will be definitely some power loss with respect to that, I square R, simple. And that power may be dissipated in the form of heat, giving rise to heat. So if this power off or that leakage power is increased, if we try to scale down device and it produces heat, it might affect the circuit performance of the entire system. গরম হয়ে গেলে কি হয়, কিছুটা অনেক ক্ষেত্রে স্লো ডাউন হয়ে যায়, অনেক ক্ষেত্রে শাট ডাউন হয়ে যায়, অনেক কিছু প্রবলেমস হয়. So we need to avoid that heat. Now if we need to avoid that heat, because the heat simply making the circuit unreliable, so we need to have some arrangement that can actually absorb that produced heat. that kind of circuitry arrangement is called heat sink. Now heat sink means what? Heat sink means we have to design it using some circuitry components, some electrical components, so that actually violates this less circuit components criteria. The circuit components is increasing in order to make this whole system reliable. So you see here itself it is creating a loop that if we are scaling down the device dimension to achieve a proper performance, we end up generating more heat, and if this heat becomes severe it leads to the unreliability of the circuit performance. So we need additional circuitry to take care of this problem, and that is violating this. So there will always be a compromise, not compromise, there will always be a trade-off between these two parameters, that how much we can actually scale down without increasing this circuit components much. So always this type of statement we give. So here there is a chance of optimization. Again, if the circuit components is more, then obviously the package density will be low. Package density low means if the IC area is fixed, now since the circuit component is increasing, we won't be able to uh, cram up more circuit components onto that particular area. It is actually decreasing the package density. And if we won't be able to uh, place more a number of circuitry, we might miss some of the functions. We might not be able to put all the functions on that particular IC. So multifunctionality will get affected. And also, if we manage to put all these things, all the circuit component to achieve the multifunctionality, but we end up in increasing the area of that IC. So that might hamper the portability, because now the IC size or chip size is increasing. So here also we need the optimization. And sometimes if increase of circuit components means it is increasing the delay, so speed might get hampers, but less circuit component means we are achieving for faster systems. So you see from this total map, actually we are not getting any particular solution. The solution is always aim specific or application specific. So this is how the entire system, whether it is digital or it is analog, it works. So always the term optimization here comes into play. Now we have established basic 4 types of flip-flops. In 4 types of flip-flops, we have seen their workings and etc. So now we would like to establish the characteristics equation of each flip-flop. Characteristics equation means we need to write the output as a function of inputs in a mathematical equation form. So now if we consider at first SR flip-flop, suppose. So we know the characteristic table is like this. 0, 0, we are ending up to the previous state. 0, 1, the output is 0, that is reset state. 1, 0, giving the set state, and 1, 1 was invalid in case of SR flip-flop. So if now we break it down, break this characteristic table and elaborate it. So 3 variables are here. SR, I'm here for the time being, I'm discarding the clock. Throughout this entire period, you assume that the clock is enabled. So I am just discarding the clock signal here. So now you see 3 inputs are here, S, R and Qn. What is Qn? Qn is the previous term. And Qn plus actually Qn plus is the present term. It is previous and it is present. Or alternatively, this is present, this is the next state. But it is always better to say or to term this one as the previous state and this one as the present state. So when S and R is 0 and the previous state is 0, it is simply acting as memory, so the output would be 0. And for this condition, if output is 1, it will actually remain 1, because for 0, 0 it is serving as memory. Now S and R achieves this condition, 0 and 1. and previous state was 0. It will anyway give 0 because it corresponds to the reset state. And if the previous state is 1 for this combination, it will change to 0. It doesn't matter whether Qn is 0 or Qn is 1. For this combination, the output will always be 0, 0. Similarly, for this combination 1, 0, whatever be the value of the previous inputs, the output will always be 1. That is, it is established at set condition. And for 1, 1 condition, since it is SR flip-flop, for 1, 1 condition, whatever be the previous state value, it doesn't matter. The output can be 0, can be 1. We cannot predict it. So we put a don't care over here. Now, to write this Qn plus 1 as a function of these three, all we need to do, we need to generate a Carnot map or a K map. That is exactly done over here. Here it is 0 and 1 S value, and R and Qn is placed over here. So for 0, 0, 0, this condition it is 0, it is coming down as 0. 0, 0, 1, it is 1, it is coming down as 1. And then again 1, 1, 1, the condition is don't care, it is coming down as this. So after filling this entire Carnot map, we are getting something like this. How to solve it? Very simple. This one loop we are getting and this another loop we are getting. So at the output, for this loop, I'm actually getting S, and for this loop, I'm actually getting R bar Qn. So the output is S plus R bar Qn. This is the characteristics equation of SR flip-flop. Now if we go on establishing or determining the characteristics equation of JK flip-flop, we will see here. We will break down this JK timetable, not timetable, this JK characteristic table into this one. For 0, 0 memory condition, so this will remain 0 and this will remain 1 until this, for these three conditions here, actually the sixth condition, it will remain same as the SR flip-flop. Only the modification in JK flip-flop is what? It is this 1, 1 condition. Instead of remaining at invalid state as it is in the case of SR, here it is just producing toggling state. When it is 1, 1, the output simply change its state from its previous value. So it is given as Qn bar. So if for 1, 1 condition the previous value is 0, now it will become 1. And if for 1, 1 condition the previous value is 1, now it will become 0. So this is the toggle map. Similarly, if we break it down to this Carnot map, we will get this entire table. You see these two are now getting 0 and 1. Previously, these two were don't care conditions. So if now we solve this, we will get, for this term, I am getting J Qn bar, and for this term, I am getting K bar Qn. So ultimately, the output equation of this is K bar Qn plus J Q bar or Qn bar. This is the characteristic equation of JK flip-flop. And D and T, these are pretty simple because these are one input devices. So here D is 0, then Qn plus 1 is 0. When D is 1, Qn plus 1 is 1. So it is simply, this is the characteristics equation for D flip-flop. Qn plus 1 is equal to simply D. And for T flip-flop, it may apparent that since it is a toggle flip-flop, the Qn plus will simply be is equal to T bar. But you are forgetting one thing here. What is that? In addition to act as a toggle flip-flop, it is acting as a memory as well. When T value is given 0, it is actually producing, or it is actually behaving like a memory. So if previous state is 0, it will be 0. And when T equal to 0 and previous state is 1, it will be 1. Also, when I am putting T value as 1, then the output would be the complement of this previous input. That is, if it is 0, it will become now 1, and if it is 1, it will become now 0. So if you carefully observe this characteristic table or this elaborated characteristic tables, you can actually see that is giving, this is actually representing an XOR gate. So the characteristics equation would be Qn plus 1. You don't need to actually form the K map. From the pure observation, I am getting the output would be T XOR Qn. So this is the characteristic equation of Qn plus 1. Now, if you are asked to convert one flip-flop from another, it is very easy. If you are asked to convert an SR flip-flop to D, you will immediately connect these two input through a NOT gate, as we have already seen here. From SR to D, it is pretty simple. And if you want to convert perhaps a JK into T, you will simply short these two inputs. So these are pretty simple. These two we can do. But if it is the other way around, if you are asked to convert a D flip-flop into an SR flip-flop or a T flip-flop into a JK flip-flop, so what will be the approach? Here where these characteristic equations are coming into play. Suppose we are considering this particular D to JK flip-flop. Now D to JK flip-flop mean here there is a block of D flip-flop and we need to convert this entire thing into JK flip-flop. That is, we will give the input as J and K and at the output we will get the same output as in case of D flip-flop. So here D flip-flop, the characteristics equation was this, and for JK flip-flop the characteristics equation is this. Output will remain same whether it is D or whether it is the converted JK. So if the output remains same, all we have to do, we have to equate these two outputs. That is the output when it is acting as D flip-flop and the output when this is acting as JK flip-flop. By doing so, we are actually getting D is equal to this. So now this D, which is the input of this flip-flop, is now a function of J, K and obviously the previous states or the outputs. So accordingly, we connect or we make the circuit. What is D? D is J, Q and bar. So we need one AND gate, then another AND gate to design this term, to get this term, and an OR gate to ultimately do this addition operation. So here we are getting, this is J and Qn bar. Qn bar means it is getting a feedback connection from this output to here. And for K, it is K bar. So we will put a NOT gate over here. Here it is K bar and Qn. The Qn is like this. And the output of these two are odd with each other. So ultimately, we will get the required input. So here, this total block, obviously with clock, this total block is what we call as now the JK flip-flop. Here a D flip-flop has been converted into the JK1. Similarly, if the D flip-flop is converted into SR1, same logic will be applied. Then the output of SR flip-flop and the output of this D flip-flop, that should be equated. That should be equal to each other. So by solving that, I am getting this particular equation. So here D as a function of S and R. Accordingly, we have made the connections and this entire block with clock obviously as an input, we have successfully converted this D flip-flop in an SR flip-flop. So now with this set of inputs, it will behave as an SR flip-flop. Similarly, the thing can happen if we want to convert T to JK or T to SR. You can work it out on your own and you can see that whether you're able to convert that. Next comes the problem that we were talking about. We were talking about the situation when the restriction was this. During this entire enabling period, if input changes, it will affect the output. So we need to make sure that the input remains constant during this entire enabling period of a single clock pulse. That we need to discuss in detail now. This is something called one sketching and zero sketching. Let us consider this waveform first. This is a JK flip-flop and this is the output of master and this is the output of slave. Okay, master and slave, I forgot to mention that. Here, why it is called master slave flip-flop? Because here two flip-flops are used and the input of this flip-flop is actually depending on the output of this previous flip-flop. So, as if this previous stage is acting as a master and this is acting as a slave to that master. So whenever the master will tell, okay, this is the input, you work according to this will work. So that is why the scheme is what we call as the master slave scheme or MS scheme, or this type of flip flop is called MS flip flop or master slave flip flop. So here we can see the effect of glitches. This is the clock pulse. The J and K. When clock is enabled, J was 0 and K was 1. So 0 and 1, the output should be the master flip-flop output here, that should be 0 because it is 0 and it is 1. Now, suppose here, during this enabling period, due to some noise, the value of J fluctuates momentarily from 0 to 1. This kind of unwanted noisy signal is what we call as glitch. Now, since this is happening during the enabling period, obviously that will affect the output of that master flip-flop. And now it is becoming 0. Sorry, it is becoming 1 and it is 0. So output might change into 1. So when output is changing to 1, it will now continue to do so because it is falling down to 0 again. So now the condition becomes 0, 0. 0, 0 means it will serve as a memory condition. So this must hold the immediate previous stage. And what is the immediate previous stage? The immediate previous stage is 1. Why 1? Because of this glitch. So now this 1 will continue. And accordingly, the slave flip-flop will be continued. So what is supposed to be a 0 over here, 0 at the output, now due to this glitch, the output is become 1 permanently. So that is what we call, since the output is here catching the value of 1, this kind of situation is called 1 sketching. Similarly, if this kind of glitch happens in case of K, then the output will change from 1 to 0 over here. So which is supposed to be 1 throughout, now it is getting 0. This glitch is falling down from 1 to 0 and making it equal to the previous state. But here it is 0, 0 now. 0, 0 means it will hold the previous state. And what is the new previous state? The new previous state here is 0. So what is supposed to be the 1, now the output is becoming 0. And accordingly, the slave flip-flop will ultimately give the 0 output. So here, as if the value 0 has been caught. So that is why it is called 0 sketching. So these 1 sketching and these 0 sketching, these are the unwanted phenomena in case there is a glitch in any of the inputs during the enabling period of the clock. So that we need to take care of. Even if after employing or after using the master slave scheme, this ones catching and zero catching prevails. So we need to introduce some other scheme that actually ensures that even during enabling period, the input signal fluctuates, it won't affect the output. There, we introduce a term which is called edge triggered. Until now, when uh, when we were dealing with this clock pulse, this entire enabling period of the clock is responsible for any reflection from input to output. But now, if we restrict somehow, if we manage to restrict the influence part, that is the time through which it will execute. That is the time through which it will influence the output, then we can say that we have achieved something. So if instead of this whole enabling period, if we design the circuit in such a way so that only when the clock is changing its value from 0 to 1 or from 1 to 0 during this small time period only, if the change in input actually influences the output, then we are sorted. So then during this whole enabling period, until and unless this edge or this edge arrives, no output change will take place even if input fluctuates. That type of clock signal or that type of system is what we called as edge triggered. Until now, one entire level, that is the high logic level, throughout this high logic level, the output is sensitive to input change. So that is why that type of clock signal is what we call as level triggered. That is throughout an entire level, the flip-flop can be triggered. But now we are restricting it to these edges only. Either this rising edge or what we alternatively call as the positive edge, or here the falling edge, which we call as the negative edge. That type of clock signal is called as edge triggered. So here, please pay attention here, because a lot of you do a lot of mistakes when it comes to represent what kind of clock signal you are using. For edge triggered, the symbol, if you represent the flip-flop as block diagram as a single block, and here you are giving the clock signal. So for edge triggered, now it is coming as this triangular signal should be here. And when you are drawing the clock signal, that is the timing diagram, the waveform, then if you put an arrow over here, that means this is an edge triggered, and since we are putting arrow only here, the rising edge, it is a positive edge triggered flip-flop. Similarly, if we want a negative edge triggered, we will do this here. And there, for this symbol, we put a bubble over here if it is activated by clock bar. I'm coming into that, why this is given over here. And in case of level triggered, we give, if we give clock here, simply clock, then it will be a single straight line. And the waveform would be like this. No arrowhead will be there in this waveform. And if it is a clock bar, it is fed over here, then it is given, a bubble is put in front of this input. So this is the symbol of the negative level triggered. Now, so far we are cleared about level triggered and edge triggered. Now, what is negative level triggered or maybe negative edge triggered? Before going into that, we need to discuss additional two inputs of the flip-flop. So far we have seen the data inputs and the clock input. Now, another two inputs are going to be introduced. These are called preset input and clear input, alternatively set input and reset input. And these are called the overriding inputs. Now, overriding inputs means what? It is overriding something. From the name, it is clear that it is overriding something or overwriting something rather. What it can override? It can only override the already existing input, or in short, it can override the data input. So if this present and clear are introduced within a flip-flop circuit as the third and fourth input, maybe like this, there, if the preset value is set 1, the preset value, if it is activated, not set 1, if it is activated, then whatever be the value of data input, even it is set to as s equal to 0 r equal to 1 or j is equal to 0 r equal to 1, which is supposed to give the reset state, but since we are setting this preset, we are activating this preset pin, now it will give the set state at the output. Similarly, if we activate the clear input, whatever be the value of the input, it does not matter, it will give the output as a reset value. It will give a reset state. Now, what are the significance of these two? Sometimes it might happen that due to some kind of malfunctioning, circuit malfunctioning, suppose the entire sorry, suppose the entire flip-flop we need to clear the previous data. So what we will do, we will just simply activate this clear pin. In that way, all the outputs will just fall down to 0. So we have cleared it. Or it might happen in some case we need to achieve the output as 1 or to fix it at 1. In that case, we can easily set this or activate this preset pin. So that is the significance of using these two additional pins. Now here two things are written. I have not said that if I give the preset value 1 or clear value 1. I have used the term if we activate this pin and activate this pin. Now this can be activated in two ways. If it is getting activated when we put or when we set this pin as 1, it is called active high circuit. Active high means when I am giving 1, it will perform the desired operation that it is supposed to perform. So it is getting activated. And if it is getting activated when I am giving a signal 0 or a low logic level, then we call this preset is active low. That is, to activate it, we have to give the input pin 0. Similarly for clear, this is active low when I am setting this pin is equal to 0 or logic low, it is active. And it is when active high, when I am setting this pin high or to logic level 1, it is getting activated. So these are the significance, or these are the internal mechanism of a circuit being active high and active low. Now let us come down to this positive level triggered, positive edge triggered. Now positive level triggered is very simple in the sense that during the positive half cycle or during the enabling period of this clock, the circuit is actually being able to be triggered. So this one is called the positive level triggered. And when it is called negative level triggered, that is if I am giving a logic level low and somehow the output responds to the change in input, in that case, we will say that it is negative level triggered clock. That is, for the disabling period of the clock, the output is actually responding to input. Similarly, for edge triggering as well, it is called positive edge triggered when the this edge is responsible for reflecting the change in input to output, and throughout the rest of the clock pulse, it won't respond to input. Then only it is the rising edge or the positive edge. We call it as positive edge triggered clock, or The flip-flop that runs, that is used using this positive edge triggered scheme, we call it positive edge triggered flip-flop. Similarly, negative edge triggered, when we call it negative edge triggered, well, it will respond to change in input at this edge or at this edge simply. We will call it negative edge triggered flip-flop. So now we have established all the inputs that should be present in a flip-flop. So what are these inputs? One is data input. That could be 2 inputs or 1 inputs depending on the type of the flip-flops. Then there are preset inputs and there will be clock input. Preset and clear, that is called the overriding inputs, and there will be clock inputs, and 2 outputs are there. So this is actually the input and all the inputs and output pins of a flip-flop. Now you see in several books, this symbol is very confusing. Sometimes in some books you will find this kind of symbolism, that here a bubble is placed, here a bubble is placed. That means this will be activated when we put a logic level 0 over here. So basically this is an active low overriding inputs. But here this should not be given, at least the bar should not be given here. So in this case, if you want to denote the preset and clear pin, it will be something like this, that preset bar here and clear bar here, because here you are given preset value, okay, but here it is actually getting the complement of what is given over here. So basically, based on that symbolism, we are mentioning this preset bar inside this block. So that should be the proper way to use the symbol or to write it. You will get it more clear when you will learn about counters. But please note that if you denote this pin as preset bar, that means here you are actually getting the complement of preset bar, that is you are actually getting preset over here. So that type of confusion will be there in many books. It is a bubble is put here, but here it is denoted as PRE bar. So it should not be PRE bar over here, it should be PRE bar over here. So in this way you should symbolize a total flip-flop using the overriding inputs. Now this is the last problem today that we are going to study. This circuit is given, and here for the first time we will see the effect of delay. That is the delay through gate, the gross delay, the propagation delay from input to output through a gate. It is not the gate delay that corresponds to the gate of a MOSFET. That gate delay is not that. It is in circuit level, the gate delay. And that gate delay is the device level gate delay. So here this circuitry arrangement is given to you. And you are asked that prove that this circuit behaves like a positive edge triggered JK flip-flop. So actually what you are asked to do, you are asked to do to show actually that at the positive edge of this clock signal, the output changes from its previous state, or output not changes from its previous state, not necessarily, but output is actually reflecting the input over here that is needed to establish over here. So here let us assume it is given some initial condition. What is the initial condition here? Suppose J is given at 0 and K is given as 1. And the initial output, from the output that we are going to start with, that is given Q is equal to 1 and Q bar is equal to 0. Okay. So here what we need to show, since J is equal to 0, K is equal to 1, the output should now take the form of Q is equal to 0 and Q bar is equal to 1. And that change from this state to the reset state. That change is actually happening at this edge, that it is the at the rising edge of this clock pulse that we have to establish. Obviously, after suffering some kind of delay, because here we are considering the delay. The first step of that is to give the names at each of the output. So we are giving the names as A, B, then C, D, E, F, and this is the Q and Q bar. So we have named it. Now we are going to draw the waveform for each of this point. What is the waveform? So at first, we are drawing the clock. This one. It is simply like this. Now we have to show that at this edge, the change of state is taking place. That is, Q is changing from 1 to 0 and Q bar is changing from 0 to 1. Why? Because the previous state is given as 1 and 0. If the previous state would be like 0 and 1, then the output should be maintained after this positive edge. So depending on that, we will draw the entire waveform. So this is the clock, this one. Now here you see C, the same clock has been fed, only it is coming through a NOT gate. That is, it is the clock bar signal. So here the clock bar signal will be something like this. Why something like this? Why this gap? Because it is actually traveling through a NOT gate. This gap is actually corresponds to the gate delay of this NOT gate. Next, straight coming down to E. E will be just the replica of this clock signal, this one. Why? Because here we are ignoring this wire delay. If we consider the wire delay, then obviously there will be some delay. But for the time being, we are ignoring that. So it will be like this. Next, we will see what will be the output of this gate. Now, what is this A? This A is nothing but J Q bar C. J Q bar C. This is an AND gate. So if any of the inputs is maintained at 0, then the output will always be 0. And here the initial condition, the condition is given that J is maintained at 0 and K is maintained at 1. So here one of the inputs is 0. So at the output, we will get A is equal to 0 throughout, because 0 is maintained over here. Now let's coming down to B. What is B? B is simply this K, C and Q. So K, Q, C. K is maintained at 1. C is maintained at, we don't know. It might change. C basically the clock bar signal over here. And what is Q? Q is here maintained at 1. So this entire thing will actually depend on how C is changing. Here, this is C. We have given the name. So here C is actually the clock bar. And it is getting from 0 to 1 at this edge. So when this clock, this C will transform from 0 to 1, all the inputs of this gate will be 1. So the output B should be 1. So this is changing from 0 to 1 here, and this edge will actually be reflected here after a certain delay, and this delay is nothing but the delay corresponds to this gate. So B here will change its state from 0 to 1 and it will follow. Next, we will go to D. What is D? D is simply AE whole bar. Okay, AE whole bar. This is a output of this NAND gate. Now here, since one of the NAND gate, if one of the NAND gate is 0, then the output should be maintained at 1. And here it is a function of A, it is AE whole bar, and here A is maintained at 0 throughout. So D will be maintained at 1 throughout. So up to this, it is done. Now let's come down to F. What is F? F is BE whole bar, that is these two inputs, B and E. This yellow one and this yellow one, this B and B. So both of them actually are changing at some point of time. But you see, this F will only fall to 0 only when both of these input, both of these inputs will become 1. If one of the inputs will remain 0, either this is 1 0 or this is 0 1, the F will be maintained being at high state. That is exactly what is happening here. You see, here and here, if we go on until this stage, either E or B, one of them is maintaining a 0 value. So up to this point, this F will be maintained as 1. Now here what is happening, here E is going from 0 to 1. So now it is becoming 1, 1. So this, now F should come down to 0. And this edge will be reflected here after suffering this amount of delay. And this amount of delay is actually corresponds to the delay of this gate 4. So these output and these output we have sorted. Now we will see the Q bar signal. What is Q bar? Q bar is nothing but F and Q whole bar. So if it is F and Q whole bar, then up to this, F and Q is maintained as 1. So up to this, F is also 1, Q is also 1. So Q bar will be maintained at 0. But at this point, F is coming down from 1 to 0. So here it is now becoming 0 0. So it will now change from 0 to 1. This edge, the effect of this edge will be reflected after suffering this gate 6 delay. So now Q bar has changed, and that changed Q bar will be reflected here. So if now we want to establish Q, it will continue to be at 1 here, because here D is what? D is maintained at 1, and Q bar until this point is maintaining at 0. So it will be 1, and here it is rising from 0 to 1. Q bar is changing from 0 to 1. So now the input will be 1 1, and this edge will be actually reflected at this point, where the Q will ultimately falls to 0. So you see, this is an entire clock period. Here the another cycle is there, it is not drawn. So here the positive half cycle, here is the negative half cycle, and the change is actually taking place, you see, after this age, at this age rather. And why this gap is coming? This gap is coming because it has to suffer through a number of gate delays. So total number of gate delays here 3. You see, here one gate, here another gate, here another gate. So all this effect, this is actually the rising edge or the positive edge, and after suffering this amount of delay, the effect of this edge, is actually reflecting at this point of time. So we have proved that this JK flip-flop is actually behaving like a positive edge triggered flip-flop for this given initial conditions. Now there can be a lot of initial conditions, means suppose J is equal to 1, K is equal to 0, and while Q is maintained at 0 and Q bar is equal to 1, this could be one condition, or this could be 1, this could be 0, this will be another condition. So several conditions can be there, a combinations of this and this can be there. Now accordingly, you have to draw this entire timing diagram in order to establish whether the given circuitry is behaving in a certain way, whether it is behaving like a positive edge triggered flip-flop or It might be like a negative edge triggered flip flop, or maybe level triggered flip flop, positive level triggered or negative level triggered, something like that. So the approach will remain same. All you will have to do is to draw the proper wave diagram, considering the delay in each case. And ultimately, from the result, you will actually infer what exactly is happening for a given circuitry. Now, after this, there is a concept of data lockout flip-flop. Here the scheme is the master flip-flop, here is edge triggered, and the slave flip-flop, here is the level triggered. Now, I am giving this as a problem to you to see or to verify whether this kind of waveform is coming in case of JK master slave flip flop or in case of data lockout flip flop, and why it is called a data lockout flip flop. This thing you do by yourself. This is a reading assignment for you. This is the problem. So let's stop here today. If you have got any kind of confusions, you may ask. কোনো কনফিউশন, কোথাও কিছু প্রবলেম থাকলে জিজ্ঞেস করতে পারো। কারোর কি আছে? কোনো স্লাইডে কোনো প্রবলেম, কোনো জায়গা মনে হচ্ছে বুঝতে পারছি না, একটু অসুবিধা হচ্ছে?
No, ma'am.
No, ma'am.
ওকে, ঠিক আছে। আমি আজকে একটু তোমাদের বেশি পড়ালাম, তার কারণটা হচ্ছে এরপরে দেখো একটা ক্লাস আমি নিতে পারবো না, কালী পুজো আসছে। সো প্লিজ গো থ্রু দিস ফার্স্ট ক্লাস। জেনারেলি আমি এতটা ফার্স্ট ক্লাসে কভার করি না, কিন্তু তোমাদের ব্যাচটাতে আমি এটা করলাম in the hope that you will go through this entire thing, because without understanding this you won't be able to understand the later classes. কারণ এর পরের ক্লাসগুলো যেগুলো হবে সেগুলো সমস্ত কিন্তু এই বেসিক ফান্ডামেন্টাল প্রিন্সিপালের উপরেই দাঁড়িয়ে আছে। আর ইন দিস কেস আরেকটা কথা আমি তোমাদের বলি যে ইউ আর স্টাডিং সিকোয়েন্সিয়াল সার্কিট, রাইট? So sequential circuit, it is dealing with sequence of operations, but the approach of your study should also be sequential. Sequentially তোমাকে এগোতে হবে, মানে তুমি ভাবলে যে ঠিক আছে এবারে হয়তো কাউন্টারটা ইম্পর্টেন্ট, একটা পার্টিকুলার কাউন্টার, তো আমি ওইটুকুই পড়ে নিই, বাকি ফ্লিপ ফ্লপ এগুলো আসবে না, এসে গেছে, পড়ার দরকার নেই। তুমি কাউন্টার পড়তে বুঝলে, but without understanding the mechanism of flip-flop or working principle of flip-flop, you won't be able to understand counter. তো এই জন্য এই পার্টিকুলার কেসটায় তো each class is actually related to its previous class. তো সেই প্রিভিয়াস ক্লাসটাকে যখন হয়ে যাবে একটা ক্লাস, সেই ক্লাসটাকে সেই দিনই একটুখানি বসে ক্লিয়ার করে নিও, নিজেরা একটু পড়ে নিও, যাতে করে তোমরা পরের ক্লাসটা প্রপারলি বুঝতে পারো। ঠিক আছে?
Yes, ma'am.
ওকে, একটু ওয়েট করো, আমি তোমাদের অ্যাটেন্ডেন্সটা দিয়ে দেবো, একটুখানি ওয়েট করো। আচ্ছা, টোটাল আজকে তোমরা আছো, আমি তো দুটো ডিভাইস থেকে একটা থেকে যদি আমি বেরোই, 27 জন আছো, তাই তো? ঠিক আছে, দাঁড়াও। তারিখ 2 আচ্ছা, আমি নেক্সট ক্লাস তোমাদের নেব বৃহস্পতিবার তো কালী পুজো, আমি ওই জন্য তোমাদের ছাড়ছি। কি বৃহস্পতিবার করবে ক্লাস? যদি তোমরা করো আমি নেব, নাকি বৃহস্পতিবারটা ছুটি হলে ভালো হয়? সব চুপ, কেউ তো বলো।
ম্যাম বাড়িতে পুজো আছে।
আচ্ছা আচ্ছা, ঠিক আছে, তাহলে বৃহস্পতিবার দিনটা আমি তোমাদের ছেড়ে দিলাম। শুক্রবার দিনটা একটুখানি কষ্ট করে এসো। শুক্রবার আমি 10টা থেকে, আমি সকালে ক্লাস নিয়ে ছেড়ে দেবো তোমাদের, ঠিক আছে? শুক্রবার 10টা থেকে আমি তোমাদের ক্লাস নেব। ওকে
Yes.
ওকে, ঠিক আছে, থ্যাংক ইউ, লিভ করতে পারো তোমরা।